So we've got 3 topics left. This one here on special triangles is really kind of a precursor to some of the stuff we do in grade 12. We'll still obviously test on it right now, but it's more going to matter later. You know how I mentioned before I hate how they teach trig where you do like a little in each section here? I find this one frustrating because to me this one doesn't really fit with what we just covered. It more fits with where we're going, but this is where they decided to put it. So just so you're aware, this is something that is very, very critical information for next year, and yet we assess on it like a little bit this year. So don't forget this if you can avoid it. So these are known as the special triangles, not just regular triangles, but the special ones. I like the colors here. Okay, you guys remember how I've been talking since the beginning of this unit about how triangles are Telemonster's favorite thing because of the 3 sides and 3 angles? It's kind of the main concept. For you guys, especially the ones in physics, you'll probably appreciate the idea here about how sometimes we need to use exact values. On the first assignment, I was pretty lazy on the answer key in terms of my rounding. I was just pretty wishy-washy, 11.4, close enough. But, I mean, that's not actually acceptable, right? In terms of being precise, you don't just say round to the nearest tenth. If we'd like to do it properly, we have to use every single digit if possible. So today we're going to talk about how to work with the special triangles that give us exact numbers, not rounded numbers. And I want to start off with just a basic example, which actually is similar to what was one of your old assignment questions, the baseball diamond one. Baseball diamond is actually a square with a length of 90 feet across each side. Green might have been a poor choice. You guys see that well enough? And here's what's going to happen. You're going to throw from home plate to second base. Basically, the guy's going to try to steal second. You're going to try to throw him out. And hopefully you guys can kind of visualize. There's a triangle in there. See that? But here's the change. This is what differentiates the kids that take dash 1 from dash 2. Rather than just saying, find about the distance rounded to the nearest tenth, what I want for you guys to calculate is, what is the exact distance of that hypotenuse triangle from home base to second? Does that make sense? So if you were doing this exactly without rounding, you'd say something like, well, c squared equals a squared plus b squared. C squared equals 90 squared, because that's like this side here. 90 squared, that's this side here. What I would have shown with the dash 2's is do something like this. 90 squared plus 90 squared, and then you'd square root it. And I'm guessing what most of you guys did on your assignment is you probably said 127. You might have said 127.28. But do you guys agree with me, though, that there are more digits behind that? And if you were to do this properly, we need to carry those digits over for forever. Right? Now, if you have a graphic out there that can go back up and find that number, that's fine. But we don't always have that ability. Does that make sense? So what we need to find a way to do is take this number right here and call it an exact value. And I'm just going to go back up a step. See how this number here was 16,162,200 or 16200? You could have said that that was an exact value. Only that's usually not how we end our answers. We would usually try to reduce the square roots. You remember doing this from a previous unit where I could say this is equal to 162 times 100? Why did I pick 162 and 100? Yeah, so you could call it 10 root 162. I bet you I can go better than that though. 162. Need to try some more numbers here. Maybe you can. 162 doesn't divide by 4, it does divide by 9. Actually, it divides by... Oh, it divides by 81. That's even better. You could do say 81 and 2. The reason I picked 81 and 2 is that 81 square roots to 9. So, long story short, if you can kind of follow where I'm going here, this would be the exact value. Don't write 127.28 repeating, because that's going to cause you to lose precision in your decimal places. And then if you guys know the words precision and accuracy, if you start losing how precise you are because you've stopped using so many digits, eventually if you multiply multiple calculations together, you'll start to become inaccurate. Right? Rounding consecutively causes issues. So my goal today is to help show you some tricks so that you can find your answers in what's an exact value form rather than a rounded form. So like on the previous assignment, I was pretty like, meh, you're close enough. We need to go back to actually tightening things back up again and finding so that we're not actually rounding. Does that make sense? Okay, here's another example. We have a golfer. By the way, if you're thinking and wanting to think of examples for your research, for your project thing, you can like kind of use some of these. Sports is great for trying to find this. Right? Sports has angles everywhere. The golfer here is going to have a 35-inch long golf club. So that meant from like here to here, it's supposed to be 35 inches. And then he hits the ball with a nice, perfect 60-degree angle. My question was, determine the exact height of the golfer's hands above the ground. So
Mr. Perry, can you please go to room 116? Mr. Perry, room 116.
See how this side in purple right here is the exact height of his hands above the ground? So first I want to show you what we did beforehand, and then I'm going to show you how we're going to solve this issue otherwise. This is a nice right angle triangle, right? So you'd say, well, this is the opposite, that's the hypotenuse. You'd say the sine of 60 degrees is going to be the opposite over 35. You'll times up the 35 and go 35 sine 60 equals the opposite. You then would go to your calculator, you'd type in 35 sine 60, and it would give you this answer right here, which is not wrong, but I mean, you have to round at some point. What we'd like to do is try to find a way using our math ability, not so much from a physics point of view, but more from a math point of view, to try to write this number right here in such a way that it doesn't require like a decimal irrational number. Does that make sense? So some kids suggest, well, why don't we just leave it at this? And that's not wrong. Like, I guess that is an exact value, but I have another trick I want to show you. So I want to come back to this in a second. So just leave that. You guys okay with that up to here, though? Okay, so let me go to my next slide and we'll come back. These are known as the special triangles. Someone really brilliant, could tell you, but someone really smart came up with the idea of trying to find a way to make a triangle ratio work for 30, 60, 90 triangles and 45, 45, 90 triangles. Just because those are some like common numbers you might have, if that makes sense. You know, like this side right here, for example. Let's use the 45, 45 one. Let's say that this side right here was 1. What would this side over here have to be? Why? It's an isosceles triangle. And isosceles triangles have a property where this angle and this angle, if they're the same, these sides are to be the same. Well, it means then that this side length right here is going to be root 2. The reason why is that using Pythagoras' theorem, 1 squared is 1. Plus 1 squared is still 1. When you add them together, you get 2, and then you square root it, the side is root 2. Well, what would happen then if this triangle was not 1 and 1 and root 2? What if this triangle right here, what if this side here was 30? Well, then this side right here would also be 30. This side over here would be 30 root 2s. I just upscaled everything by 30. If this side over here was 69.4, then this side over here would also be 69.4. This side over here would be 69.4 root 2s. Well, this was a clever way to get an exact value using square roots. Did you follow how I pulled that off there? Now, that triangle there is actually not useful in solving our current question, because our current question involved a 60-degree triangle. So let me help you out a little bit with this one here. To solve this one, I'm actually going to pretend that this triangle was continued on both sides here. Imagine this was actually like a large triangle. If this was 60 right here, this would also be 60 right here, and this would be doubled to get you 60 as well right there. pretend that was what the triangle was. What kind of triangle? What's the special name for that? The equilateral. Okay. Now, this may seem strange to write it like this, but I'm going to call this side length here 2. I have a reason for why I made it 2, not 1, but go with it for right now. That's a 2. What would this length from here to here then be? 1. That's actually why I chose that, because from here to here is 2, here to here is 2, but then from here to here is 1. Okay. Well, now that I've done that, now I'm going to actually just erase the old triangle edge here. So, I mean, I know you maybe drew it, just don't erase it yourself. If this side right here is 1, this side here must be double it. This side over here is actually root 3. And the way I calculated that is 2 squared is 4, minus 1 squared. 2 squared is 4, minus 1 squared is 1. 4 minus 1 is 3. Square root it, get you root 3. Here's why this is useful then. If this was a 1 and a 2 and a root 3, well, then those are your sides. But let's say this side right here wasn't 1. Let's say this side right here was 50. Well, then this side over here would be 100. And this side over here would be root 3 times 50. Isn't that clever? So rather than having a decimal value, we're able to figure out in terms of square roots. So let's take that principle now and let's go back to this triangle right here. This side right here was 35, right? If this is a 60-degree triangle, I can use that same principle of like upscaling the triangle, and I can tell you that this side right here would be 17.5. Why is it 17.5? Well, because it's half. Which means that to answer my question right here, you guys figure out what this one's going to be. Your opposite side has an exact value. Do we see that? Yeah. These two things are equivalent to each other now. Right. And just take a calculator, test it. If you take 35 and times by the sine of 60, which is what we would have done earlier, you'd have gotten 30.31 repeating. But an alternative math way of solving it would be to call it 17 root 5 root 3's. Not going to get you the same thing. This is preferable because it's an exact value, right? There's nothing rounded about it. It's a value that we can work with, and you shouldn't be too afraid of it because it's just got a square root of it. Right? We work with square roots plenty. We wouldn't do this in my physics class, by the way, right? Like, we would just, save this decimal value all the way through. We'd go back up and find it to use it again. But from a math point of view, this is kind of clever, isn't it? So that we can just save it that. Here's that triangle one more time. You just need to memorize this. The way it works is that this is 1. This side right here, the hypotenuse is 2. And this side is root 3. So if you upscale this triangle, you just multiply by those ratios. This could be 30, this could be 60, this could be 30 root 3. This could be pi, this could be 2 pi, this could be pi root 3. Just a nice way to make it so that it's exact. Same principle applies here. This is 1, this is 1, this is the root of 2. This could be 400, this is also 400, 400 root 2. I feel like you can hopefully have the point out. Okay, so let's try some more examples on this in a bit. I think I have some more slides between them. Oh, yeah, here we go. So kind of here's a rough idea about how you can know what each of these angles is equivalent to. Sine of 30 is equal to 1/2. Basically, if you look at this triangle right here, if here's a 30, sine of 30 is always 1 over 2. Now, it could be 1 over 2, could be 2 over 4, could be 3 over 6, could be 800 over 1600. But whatever the ratio happens to be, we know it's 1/2. Does that make sense? Sine 60 then is root 3 over 2. Now, it doesn't have to be root 3 over 2. It could be root 3 times 200 over 200 times 2. It could be like an upscaled number, if that makes sense. But that's ultimately what the ratio will reduce to by the time you're done. So this is kind of a neat little chart that you can use. You don't really need it so much this year, but we use it a ton next year. One more thought here. This one right here is not quite what you'd expect. If I were to ask you sine of 45 would be like, say, the opposite over the hypotenuse. You might be inclined to think that sine of 45 should be opposite over hypotenuse. Can you guys figure out how they went from here to there? No, they did. You guys have any idea how 1 over root 2 turned into 2 over root 2? We actually did it this year in our square root unit. It's called rationalizing a denominator. This is where you'd say take 1 over root 2, you'd times by root 2 over root 2. Do you recall this? Root 2 times root 2 on the bottom is literally 2, and then there's just a root 2 on the top. You recall doing that? So sometimes you'll see these things rationalized. What I'm going to do here is every time that I see the number sine 30 or cosine 30 or tan 30, I'm just going to substitute this in its place. That's kind of the easiest way of doing it. So you know how back here on the golfer example, how I had 35 sine 60? What I'm going to do is whenever I see sine 60, I'm going to go to the chart and see, well, what is sine of 60? Sine of 60 is root 3 over 2. So rather than writing sine of 60, I'll say it's 35 root 3 over 2. 35 divided by 2, 17.5. So it's actually really easy. It doesn't really require a whole lot of extra work. My goal here is to teach you how to work with numbers that are non-rounded. Okay, let's try another example. Ladder up against the wall. He needs to reach a window which is 18 feet above the ground, and it needs to have a 45-degree angle. We need to know the exact length of the ladder required. Here's how I like to show kids how to do it. You can do this in more than one way, but here's my preferred method. I would do exactly what we've done before. I would say, well, this is the hypotenuse, that's the opposite. So I'd say sine of 45 degrees equals the opposite over the hypotenuse. Sine of 45 degrees equals 18 over the hypotenuse. I do that. Okay, this is where I would deviate then. Most of you guys would have just taken the hypotenuse and sine of 45 and just flip them around and get an answer. But at this point here, I'm going to do a substitution. I'm going to go to the chart and say, well, sine of 45 is root 2 over 2. I'll just go find that value. Sine of 45, and I'll call it root 2 over 2. That makes sense? I've replaced the sine of 45 with its equivalency. Now I'll solve for h. To get h by itself, I'm going to need to times the 2 up, the h up, so you'll have h root 2 equals 36. I'll divide by root 2. There. My hypotenuse is 36 over root 2. That is my exact value. You probably wouldn't actually leave it like that, though. Normally, you'd be asked to rationalize. Did I go too fast? Was that something you could follow up to that point? Hopefully, you get the same thing. If you did 18 divided by the sine of 45, and you do 36 divided by root 2, hopefully you get the same thing. Chances are it wouldn't get written like this, though. It probably would get written as 18 root 2. The reason why is they would rationalize. Root 2 times root 2 on the bottom here would literally become 2. 36 divided by 2 would give you 18. So they probably would rationalize. But either this or this would be considered your exact value. That's all. Again, this doesn't come up a ton in our course. It's much more applicable next year. They love to give a lot of questions that are numeric response to them, where they would say your final answer would be like A root B. And so then you wouldn't say the answer is 25.4558, because that is correct. You'd have to answer it as 18 root 2, so like your A is your 18 and your B is your 2. Does that make sense? Okay. We've done this example before. Here is your recliner. The chair is capable of reclining up to an angle of 150. The back of the chair has a length of 104 centimeters. So let's just put some stuff in here. This angle in here is 150 degrees. The back of the chair is 104. It wants to know the exact minimum distance away from the wall the chair needs to be placed so that it's fully reclined. The chair doesn't touch the wall. You know what I'm saying here? Imagine that the wall is right here. How far away from the wall does the chair need to be set so that when you put it into the recline mode, the recline doesn't bash up against the wall? Can you see that? So this right here is my wall. My question here is, how much distance should you have there? But we don't want to round it, we want to know the exact value. In a way, if you can see it, there's a little triangle hidden in there. There's a triangle right hidden in there, where this side is 104, and we're looking for that side right there. You guys visualize that? What's the angle? Yes. Because see how this is a 150 right here? If there's a 150 right here, then this last little bit here must be a 30 and a 60 left over. It shouldn't matter which one you use. Either one should work. So you might try, like, say, the cosine of 30 degrees is equal to the adjacent over the hypotenuse. Then a little substitution trick. Rather than calling it cosine of 30, go find out what cosine of 30 really is. Cosine of 30 is a root 3 over 2. So call it root 3 over 2 is equal to x over 104. Times up the 104. 104 root 3 over 2 is x. And then since 104 does divide by 2, call it 52 root 3. That is our exact value for x, as opposed to like a decimal one. You don't follow that? So, I mean, in terms of what's new, one, a shift away from rounding, which I think most of you guys are pretty aware of that rounding is a bad thing. Right? You've been well trained on that, I hope. Two, the only other difference is if you ever see a cosine of 30, 60, or 45, or really anything, if it's an angle of 30, 60, or 45, you can do a quick little replacement of your angle to either like root 3 over 2 or root 2 over 2 or something off that chart there. And if you just do that little replacement, then you can get your answer. But your answer is now in terms of square roots. That's all. Does that work? Okay. That's all I got. Any questions? Okay. In terms of your new assignment, did you guys print it off yet? How many should I print? Like one for everybody? I didn't post until yesterday, so that's fair. Here, let me show you the assignment here in case you haven't seen it. For example, here's one that I like here. This is a golfer. I found this formula online somewhere. It's an extra physics formula I've never seen before, where the distance is equal to the velocity squared times the cosine of your angle times your sine of your angle over 16. But apparently this only works if you're in feet, I guess. It's not on our physics formula sheet, but you can still work with it. What I'm going to do is I'm going to tell you the angle is 30 degrees. I'm going to tell you that the initial velocity is 110 feet per second. So you're going to put 110 right here, and you're going to put 30 degrees here and here. Only rather than just literally typing that all into your calculator and getting me a decimal answer, I want to see whether you can replace the cosine of 30 with what it's supposed to get replaced with, and replace the sine of 30 with what it's supposed to get replaced, and find an exact value answer instead. That's all. Does that make sense? Kind of how this is going to work? So, anyways, you guys should be able to do from questions 1 to 3. We'll have to do 4 and 5 tomorrow. So if you finish that much, then you're good. So why don't I print off like 10 of these, I guess?